Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
So largely on Data Skeptic, I've taken for granted in most episodes that there's some database or some data store underlying what most of the research we cover and, interesting topics we feature take advantage of underneath the hood. A data scientist's work is only as useful as the data they have to work on. And part of the reason maybe I've taken for granted that databases are just this sort of ubiquitous system that's available is because, for the most part, frankly, they have been. A tremendous amount of research has gone into database technologies for several decades. There have been database researchers, and that's been, a very serious area of interest and of commercial investment for much longer than machine learning has been an area of commercial investment for the most part. One of the areas I always look to is banking. It's pretty much unacceptable for there to be any errors in banking. If you make a deposit of, let's say, $100, and then you try and withdraw that at two different locations at about the same time, I don't know if anyone's tested that, but I think we can all be pretty sure that the bank is smart enough and astute enough and has exactly the right technology that you're not going to be able to overdraft your account, unless perhaps they allow that by design in order to charge you some fees and things like that. But that aside, if they want to, they can definitely build a system, or at least it seems reasonable they can build a system that would prevent you from withdrawing outside of the funds available in a particular account. Largely, services like that come from different constraints available in databases. So we call this ACID compliance. That's been a topic for a mini episode that we haven't gotten to yet, and maybe eventually we will, but I guess we'll do a fast-forward version of that today here because it's very relevant to today's topic. ACID is an acronym standing for atomicity, consistency, isolation, and durability. I won't go into the deep details of what each of those mean here because, frankly, they would each individually make good mini episodes that we'll probably cover in the future, but broadly speaking, those are the four criteria that one would apply for a really reliable data store, something that gives you a persistence layer as a service. You would like for, if someone goes to store some information, that anyone who wants to retrieve it moments later would see the most updated version. You would like to think that if two people want to make an update at the same time, there are facilities to make sure that they don't collide with one another. Now, this is very important in areas, like I mentioned, things like banking, where you don't want two people to withdraw the same amount of money. Or if they do, you definitely want a record of it. You want to have both things noted and not allow maybe two very close transactions to line up and allow one to overwrite the other or something like that. Now, on the flip side of that, over the last, maybe decade or so, there's been a trend in persistent stores, what many people call NoSQL technologies. And we haven't, in fairness, covered a lot of those on Data Skeptic, but we definitely will be planning on doing some of that in the future. I'm not a big fan of that term NoSQL because I think it melds together a couple of different ideas that aren't necessarily related. On one hand, NoSQL often means a certain relaxing of that ACID compliance, that very strict sort of accuracy that a bank would require. If you go to Facebook and you like a page, I don't think Facebook is particularly concerned that the next person that loads that page sees exactly to the cent, how many people have liked the page. If there's a little bit of a delay or they see something a little bit behind what's, the most relevant number of likes to that page, that's perfectly fine. Very few people are going to notice. I'm sure a company like Facebook is fond of an idea that is often called eventual consistency. As long as the numbers kind of in time add up correctly, they're satisfied with that. So historically, there's been a great deal of investment done in building these very strong database systems that provide all these guarantees, and they're great in many applications. But at the same time, providing those guarantees requires a lot of extra work be done, and systems that have to be highly engineered to make sure that undesirable situations don't arise, and that there's error handling and fault tolerances and rollback and all these sorts of considerations. And while a great deal of really useful work has been done in that area, what I guess people started to eventually realize was there are also more broad use cases where those very strict criteria aren't necessarily required. Additionally, traditional databases have always been focused on relational databases, the things that can be stored in tabular formats. Many of you are familiar with Hadley Wickham's idea of the tidyverse, that data is organized into rows as observations and columns as features. So again, to go to the banking example, if there was a single transaction, you make one withdrawal. That's a row, that's an observation. And that observation has features. What account was it withdrawn from? Where did the money go? At what time did it happen? Where did the withdrawal originate from? And while relational data is predominantly where a lot of important, useful, very well-structured data is stored, there's also been an emergence of other sorts of persistent store or database technologies. Key value pairs, things like Redis, have become popular. Document databases, things like MongoDB, have become popular, where you can store a very unstructured idea, something that can be nested and collect a lot of arbitrary features and things like that together. One of my personal favorites is graph databases, things that can store information in terms of nodes and edges and the relationships between it, and perhaps that graph engine can service interesting graph queries, like look up the densest clique or the neighbors of a particular node. So while this has been a great sort of revolution in the database world, that we've added in all these new NoSQL formats and different ideas and ways we can store data, and different applications have benefited greatly from having these other alternative ways of storing information. And each of them can provide their own guarantees or lack thereof and relax certain constraints to gain other efficiencies. There hasn't really been a cohesive way of trying to bring all those together. In fact, on many applications, I myself have found a lot of difficulty trying to pull data from, some of it's stored in a traditional relational database, some of it's in a key value data store of some kind, some of it exists elsewhere in a graph, and you end up writing a lot of code to merge these things together, and that can be inefficient and problematic, and even on top of that, you often need a large DevOps team to manage, how are we going to make sure those things are backed up and replicated? And if you need some global consistency, you want that replicated to lots of different data centers across the planet. That has historically been a major engineering undertaking. So recently, in fact, when I was at the Microsoft Build conference, this was my first taste of this, Microsoft announced a new system they've designed called CosmosDB. Cosmos reports to be all of those things in one. It's a globally distributed database system. It stores relational data, key value data, document stores, and graph alike. For me personally, even though I have definitely an interest in database technologies and how they work, and I think that will always have to be true, we've done some mini episodes on things like Paxos and the CAP theorem that are important results in the database world that really developers and data scientists should be aware of, because they're going to affect the types of systems we want to build and the degree to which those sorts of systems can be consistent and reliable and have all those sorts of properties we'd like them to have. Ultimately, I personally would like to treat a database like a utility, just like the electricity in my home. While granted, I'm sure there are some hardworking engineers making sure the electricity works, I just want it to work. I don't want to have to ever worry about it, and I'm going to be real mad when the electricity goes out. That's ultimately how I would like to perceive my databases. Now, today I don't have that luxury. I do a lot of maintenance of my own systems and monitoring, even when, the disk is filled up. In fact, this happened recently on dataskeptic.com. Our log drive filled up, and I got an alert, and I had to go and clear that out. And if I hadn't, maybe the site would have gone down or something like that. But there are definitely some movements towards having database as a service, putting it in the cloud. Now, that's not necessarily anything new. There's been some solutions like that around for a while. But as far as I know, Microsoft's offering of CosmosDB is the first one that claims to provide a very schema agnostic system that exposes APIs that provide all of these database type facilities: relational tables, key value stores, graph, document stores. And whether or not this is the system you want to migrate to, it, for me anyway, is definitely a sign of where things are going. CosmosDB is a first in many ways, so I was glad to have a chance to speak with Dharma Shukla, distinguished engineer at Microsoft, first in this episode, and later we'll be speaking with Syam Nair, director of Product's NoSQL Database Services, both of whom were contributors to the development of CosmosDB. So without further ado, let's get into that.
CosmosDB is a globally distributed database, and that we announced on day one of build. It's been a long journey to get up to this point. We started somewhere, I think, late 2010. The goal back then was to build a globally distributed database system which makes the data available wherever the users are. So if you think about it, the unique design center of cloud is that cloud has a footprint which spreads across the entire planet. If you build an app on Azure, you get automatic distribution of your app wherever Azure data centers are. So effectively, if you deploy your app on Azure, you can reach all users all around the world. But what about data? Data is stuck. Data is in a single region. Data has to be globally distributed as well, so that your application front ends can get access to the data in every region. That's the main premise, how to make data available close to where the users are. We set out as two, we had two slogans back then. First is that no data is born relational, and the other is that all data wants to be globally distributed. Those were the origins where we wanted to build this planet-scale, globally distributed database system which enables turnkey global distribution. So it automatically replicates all your data across all of the data centers. The users across the world get a single system image of your table. So effectively, you can scale throughput and you can scale storage on a single table, and the table in turn is distributed worldwide. You can elastically scale up, scale down throughput, you can add more storage, and it transparently grows. The result of such a system is that users across the world get really low latency access to your data. The users get elastic scalability of throughput and storage. Users don't have to worry about, one of the novel things about the system is that they don't have to worry about indexes or schema management. Because if you're building an app which is using a globally distributed database, as your app evolves, you don't want to deal with schema upgrades and schema versioning, and you cannot run alter table at such massive scale. You cannot do drop indexes and blah, 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 right? As a part of this, we had this challenge of also designing a database engine which is fully schema agnostic, which can ingest large volumes of data around the world and automatically index everything that it ingests and serve beautiful SQL queries, right, at really low latency. And these were not the ideas that were like we cooked up. These were rooted in the pain points that we were seeing inside Microsoft, where large internet scale applications at Microsoft, they all wanted a globally distributed database system. They all wanted 4.9 availability, single-digit millisecond latencies at the 99th percentile, elastically scaled throughput. So we had to come up with a set of consistency models that allow you to that provide clear, precise trade-offs between latency, availability, consistency, and even throughput, because these are all related. These were all the things that developers inside the company, inside Microsoft, were facing. So we started out first as let's build a system to address the pain points of internal applications. And very soon in this journey, we realized that these were not unique to Microsoft.
I wanted to cut in here and just emphasize that point a little bit because it's particularly interesting to me. While, as Dharma said, these problems might not be totally unique to Microsoft, they certainly had needs and demands to deliver on certain technological requirements that aren't necessarily common at a lot of places, and there aren't necessarily standard technologies to solve them. Amongst many other products, the Xbox network in particular is something that's very high volume and high velocity and globally distributed, and the needs of a system like that present problems that have to be solved maybe for the first time in certain ways. I think there's actually a much broader and interesting topic here about when companies face unique needs and have to develop novel solutions, how that can be an impetus for innovation that ends up being beneficial in other places in unexpected ways. CosmosDB is a very interesting example of that. Most of the time, developing such a globally scalable system like that requires a certain amount of trade-offs, and identifying what those are and keenly deciding where you want to innovate and where you want to put constraints can often be what makes or breaks a system. But one of the things that's interesting that Dharma and I got into a discussion about here is how exactly they dealt with schema. In my experience, you would often do very calculated deployments, which were kind of a pain, to be frank with you, in order to make any sort of, alter or schema change to a database. In fact, most of the time, people tend to avoid those like the plague, and they find weird ways to hack around them, reuse columns in, unideal ways, or establish attribute value pair kinds of relationships that don't necessarily belong that way in the relational database. So I was a little bit surprised to hear that they had pushed strongly for a schema-free approach when building CosmosDB. So let's get back into that discussion.
Schema-free comes at some cost. Schema-free means what about indexes?
Right.
So you can do key lookups, and that's about it. But then if you want more fancier queries, you need to manage secondary indexes. Mm-hmm. So NoSQL databases, as they evolve, they ask customer developers to create secondary indices.
Yeah.
Right? What we want, and then on the other extreme, you have SQL databases which are full schema first, fully relational, fully schematized, and they support blazing fast queries. So what we wanted to do was that we say, well, can we be fully schema agnostic? We can automatically index everything that we ingest, just like the information retrieval systems do, just like the search engines do. Can we do that and serve blazing fast queries without ever having the developer to manage schemas or indexes, or never require that from the users? In fact, we can extract schemas if they want it from a completely schema-free world, if they want it for visualizations or whatever, but intrinsically we want it to be schema agnostic. A lot of hard work went into designing an engine which, regardless of the data models that we support, be it graph or documents or key value, column, family, and so on, we wanted to be truly schema agnostic. So we harvested a lot of research that happened in other areas, in IR and other fields where those were never sort of mapped to these kind of globally distributed database systems. So we sort of mapped those ideas and idioms, harvested the best, try to operationalize it over a number of years with first parties and eventually with external customers. And so that was a very unique thing about this, and we navigated those constraints of how to optimally index everything without bloating the storage, without compromising the query performance and so on.
One of the other things that really caught my attention was, as you said, it's indexing everything. I've, on many occasions, bumped into the problem of, primary key and sort key just don't solve my situation anymore. So I think it's log n for insert. If you're indexing everything, n columns, n log n, I guess. So it's efficient, but it has a cost. How do you keep things managed when, to index everything sounds almost like magic?
Yeah, so one of the insights that we got while we were sort of, mining for ideas is that we found this unique insight, which is that imagine you are writing on a partition. You're sort of inserting or replacing, deleting records. What we found was that if you take some window of time, let's say 5 seconds, within a 5-second window, we take every record that you're inserting or replacing or deleting or upserting or whatever you're doing, we take that record and turn it into a tree. And so imagine you had let's say a key value or a JSON or a graph. We have algorithms to map it and turn all of the labels, the text representations that you sent us into a tree structure. We materialize, these are tree objects in memory. And within that window of where every label in your text in the record, effectively every column in your record became a node in the tree.
Okay.
And the column names became also nodes. And it's completely schema agnostic. So every time you insert a new record, it can have completely arbitrary set of columns. We don't really care. Your column names could be GUIDs, and the record values could be GUIDs too, right? We don't care. And we turn all of those things into these trees. And what we found is that in a small enough window of time, like 5 seconds, when we materialize all of the trees that records that we ingested into trees, we find that the interior nodes of these trees contain all of the common stuff. Because if you say, name equals Kyle, name colon Kyle, and city colon Seattle. The name is a root, a root then has a name child and a city child, and name has a Kyle child and city has Seattle as a child, right? But if you have the second record that comes in very quickly, it is likely that name and city are going to be there. It is also likely that maybe there are some other fields, but the root is always there, of course.
Sure.
And so the variance is largely concentrated at the leaves.
Yeah.
But the interior nodes, there's a lot of commonality. So what we do is that we cut the paths from the root to the leaves, and then we dedupe all of the interior nodes so that it becomes a highly compact representation. And then even the paths are very highly encoded. And then we do large flushes, 16 MB flushes on this. These are sequential writes. Effectively, we don't really require any schema. We have turned it into a sort of a schema-neutral data structure where we are just operating on trees.
I'm curious about the inner workings. It sounds like I can kind of set it and forget it in a lot of ways. Is that really the pitch to developers and data scientists, that they no longer need to worry about indexes?
We say that we want to make the heart of our systems sort of value prop is that we want to make global distribution turnkey. You don't have to worry about provisioning machines or data center capacity or setting up replication topologies across clusters of databases. And you just create a single table or a collection, and you associate a set of regions with it, and we make that completely turnkey for you. You can when the disasters happen, when you upgrade your schemas, anything that you want to do when your database is globally distributed, how we can simplify your life. For example, dealing with schemas, or dealing with consistency, or dealing with latency, or testing your own application stack in the event of a regional disaster. And we allow you to test it at any time. You can say, I want to simulate a disaster. So how we can provide these building blocks and these easy to use switches, if you will, or dials, using which we make it like completely turnkey. And so I think being schema agnostic is a requirement, we feel, when you're building a system at this massive scale.
I also had the chance to speak with Syam Nair, Director of Products NoSQL Database Services Azure at Microsoft. He helped me get some additional perspective on CosmosDB, and I'm going to share that interview with you guys now.
In 2000 to 2010 timeframe, when Microsoft was actually evolving and moving into this cloud-first, mobile-first world and building a large-scale internet applications, ourselves internally found a need for having a data store that was globally distributed. How can I actually make sure data is available as close as to the user? How can I make sure elasticity of compute and storage is limitless? How can I provide fast, responsive, single millisecond latency in terms of data access, and at the same time make sure data is durable, consistent, and it is correct throughout? This evoked a lot of our researchers, and we have about 50 plus years of actually doing distributed systems and databases we've been building for years, bringing that together in terms of how can we really build a globally distributed database. Since then, Azure Document DB, or that particular innovation, has evolved significantly in terms of, for example, horizontal partitioning across the globe, making sure that we have 5 different consistency models. So it's not like strong or perfect consistency that some of the relational systems provide, or the eventual consistency that some of the NoSQL systems ask for. We have much more well-defined consistency models. We built in 4 nines of availability, consistency, throughput guarantees, as well as 4 nines of SLA for P99 of all our queries and reads in terms of millisecond latency. So all of this together, we have been working on it for long. We added capabilities to actually have key value access. So we wanted, like, if your data model was key value, not just document, if your data model was column family, or if your data model was graph, we wanted to provide support for that. So that innovation came along. And then lastly, we also wanted to be where the developers are. So if you were using a particular kind of framework or API or any kind of open source system, IDEs, etc., we wanted to be there. So we also made it multi-API. So all of this together is what we released today as Azure CosmosDB. Any kind of cloud scale application, be it IoT, gaming, personalization, even today's enterprise applications have a globally distributed user base. When you're looking at this cloud scale or internet scale applications, and then you want millisecond latency, it's impossible to do if your data is stored in one place, because there's just network latency from a continent to the other continent. Right. With Azure Cosmos DB, you can automatically replicate your data across all Azure regions. So you as a developer can have the database created in one region and automatically replicated across 30 plus regions, and your applications can read data from as close as it's to the user. So this enables us to provide millisecond latency. So that's the primary scenario in terms of how developers are using Azure Cosmos DB. There are a wide range of scenarios, including the one you talked about in terms of data science. We provide Spark API, Spark SQL on top of Cosmos DB, but there's a wide range of scenarios.
One of the features that caught my attention the most was this multimodal concept of Cosmos DB. I've worked on a lot of projects where, of course, we have relational database, but then there's Cassandra and Mongo and Redis and thousands of other things, who knows, well, maybe not thousands, but lots of other things and headaches to coordinate them all. Is Cosmos simply providing me a single API, or are there additional benefits as well?
Yeah, so I think our view is, if you really look at the modern applications, it's very hard to model the data in the old school tables and rows. As our founder just mentioned, no data is born relational, so it just doesn't become, you have to think about modeling it. The modern applications, especially internet scale application, would rather have the data in the way it is formed and the way that the data is required by the application. So what multimodal actually provides is, look, if you really want key value data, you can store your data in a key value format. If you really are looking at a column family, you can actually do that. If you really want to store it in a JSON document, a hierarchical JSON document, you can do that. In all of these cases, you'll actually get the benefit of the engine as well as the global distribution capabilities I talked about. So the benefit of the engine in terms of automatic indexing. So if you want rich query capabilities, you need not worry about adding secondary indices. Imagine having to manage secondary indexes or migrating indexes across the globe. Like even doing at a single database level, it's very hard. And database administrators and engineers and architects often spend a lot of time perf tuning and building secondary indexes. You don't need to do any of them for any of these models. Now added to that is, one of the scenario we have seen is most cases, the modern applications start off with a particular model, then they evolve into something similar to like a graph model, relationship in terms of objects and entities that they have, how they traverse it, because that's real life, right? So we also support the graph model. So the multi-model capability enables you to actually store the data in whichever model you want in any container, in the container that we actually support. Now, regards the API, our view is CosmosDB is all about choice for the developers. So if you are familiar with, say, SQL dialect, if you are familiar with JavaScript, if you are a MongoDB user and you'll be using MongoDB and you really have built your application using MongoDB, or if you are using Graph in terms of using Gremlin and building Graph, we want to make sure that all of these work on top of the database engine, the storage engine, as well as the query layer that we have actually built. And you should not worry about any of these aspects of it, as well as the API layers. You should only worry about, as a developer, in terms of what is the value you have to add to the business. We have, as I said, JavaScript, DocumentDB, SQL. We added support for tables, and we added support for Gremlin for Graph today. We have support for MongoDB via protocol. We also, in the future, are looking at all the other open source APIs. You mentioned a few like Cassandra or HBase. These are not roadmap items I'm disclosing, but our view is that we want to make sure that if you're familiar with Cassandra or HBase, you should be able to use CosmosDB, not having to worry about and get the entire benefit of the CosmosDB ecosystem. So it's a multi-model and multi-API. That's our view.
So one of the bullets in the keynote that really surprised and impressed me was that it seems to be you can configure the consistency option you want. It sounds like Cosmos, I can configure it to suit my use case.
Yes.
And that's the first time I've really seen that in a technology. Could you tell me a little bit more about what options are available?
And I think, as you said, if you are a globally distributed database, or if you're a database that is partitioned by any kind of network, you have to deal with cap theorem. There is nothing, there's no magic, right? We have, even if you have any other vendor say, look, we have figured out how not to navigate, we have to navigate cap theorem. So that's the fact of life. Our unique approach is we let the developer choose the consistency level. So correctness of the data is defined based on each of the scenarios, right? In our own observations, what we have seen is with this 5 well-defined consistency levels that goes anywhere from strong to eventual. And generally, if you look at many of the other databases out there, you will see perfect consistency or strong consistency to be one choice, and the others talk about eventual, right? But in our observation, and we are one of the fastest growing Azure services, and we are probably powering a very large set of Microsoft's internet scale applications. So we have a large pool of data to look at. What we have seen is it's a very small single-digit percentage of customers who actually choose strong consistency level, and even smaller single-digit of customers, I think 3% or so, that actually choose eventual. Most of them are in between in terms of bounded chainless to consistent prefix to session, right? And we can take examples of it. If you think about you building an e-commerce application, and in most cases, see, you're adding something to a shopping cart and I am adding something to a shopping cart. I want to make sure my shopping cart is consistent. You want to make sure your shopping cart, or the developer wants to make sure our shopping carts are consistent viewpoint. But do I really look at, when was it added to your cart versus my cart? No, because I don't have any visibility of your cart. You don't have any visibility of my cart. So think about something like that. Most of our applications have some level of session, and you could choose a well-defined consistency level like session. So what we have done is these 5 consistency levels are based on what we have observed in the field, what we have actually seen, what customers use it for, and looked at some of the scenarios and said, look, these are the 5 choices of consistency levels we need to provide. And it seems to, in terms of IoT applications, gaming applications, retail, finance, insurance, a lot of industries, we have seen that this level of control seems to work. Over time, if we actually find that we need to provide better control in terms of more than 5, we may end up doing that. But I think that's our approach is, let's look at what the developers really want. Let's make it available to them so that they can actually control it. Make the trade-off in terms of availability versus consistency, latency versus consistency, or throughput versus consistency.
Well, and to wrap up, are there any interesting use cases you've seen in, I assume there's been some beta rollouts and testing?
More than beta, as I said, Azure Cosmos DB has been in works for a very long period of time. And additionally, we released it as a fully GA service, DocumentDB, a couple of years ago. We have significant amount of use cases in there. Some of the core ones that come to mind is IoT scenarios. We have, I could use examples of Toyota, one of the largest car manufacturers, actually uses DocumentDB for a particular solution where fast ingestion of the data that's coming from these cars and then building solutions on top of that was super important for them. And this limitless scale, the distribution of data across the globe, some of the reasons why they looked at a globally distributed database and they're using DocumentDB. Johnson Controls in a session today talked about how they leverage DocumentDB. These are all IoT scenarios. So IoT seems to be a very hot market where they are actually looking at a globally distributed database because volume of data, the velocity of the data, and the variety of data that is coming in, they really want it at global scale, and they are leveraging it. Gaming is another scenario. One of the customers, they're actually speaking at Build, Next Games, have actually built low latency access for multiplayer gaming scenarios where gamers can interact with each other. So that's another scenario where we're seeing a whole lot of use cases for Azure Cosmos DB. We have retail. Retail seems to be a scenario where lots of retail scenarios, whether it's inventory management, whether it is catalog building, a lot of these you can't model the data in one way. You need multiple ways of modeling data. So retail seems to be another scenario where we are seeing a lot of growth. Lastly, a few others are personalization, where you actually use these data to personalize user experiences. We are doing it internally ourselves in Microsoft, as well as a lot of the financial customers are doing that. We are also seeing a lot of use cases in terms of where you can actually, similar to the Lambda pattern, you can actually use DocumentDB as an ingestion store as well as a query store, and then with analytics on top of it using Spark or other languages. So these are some of the main use cases. It's not limited, but these are some of the main use cases that we're seeing.
Very cool. Yeah, I'm actually excited to give it a try myself, especially with the Spark connector available.
Yeah, it's very easy. Azure Cosmos DB, if you go to the portal and try it out, we have a lot of quick start samples. If you want to build a mobile application, we have a Xamarin, download a Xamarin sample, build a quick mobile application for iPad or iPhone. If you want to actually try out Graph, we have a very good graph visualization and exploration application out there. Obviously, we have other applications that can use tables, that can use document stores. And we also have what is called as an Azure Cosmos DB emulator. So if your developer ecosystem actually says, look, I want to try it out on my laptop or on my desktop, you could actually download. It's a full fidelity service emulator. It's not the exact same code, but full fidelity, look and feel just like as if you have Azure Cosmos DB on your box.
Oh, that'll be great for integration tests.
Yeah, absolutely.
Oh, fantastic. Well, Syam, thank you so much for taking the time to come by and share all your insights. I'm excited to see things happen with Cosmos.
Oh, thank you so much. It was my pleasure. Thank you.
Thank you. Once again, I want to thank Dharma, Shukla, and Syam Nair for taking the time to speak with me at the Microsoft Build Conference. I hope you enjoyed this episode on Cosmos DB. Until next week, keep thinking skeptically of and with data.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.